6 minutes and 22 seconds. Maybe I'd do better on Franklin.
What's the first thing that you do when you get a new job? Well, one of the first at least. You try to figure out the best way to get from where you live to where you work. Now, you may not be as scientifically thorough as I was, but at least you look at a map. Here's the map I made when I started working here. This H represents where I live, and O over here is my office. My problem then is to find my best way from H to O, not to be confused with H2O, which is Lake Williams over here. Anyway, you can see that there are lots of possibilities. I could start out on Pine, go 2 blocks down Franklin up to Alumni Drive and into my office, or I could go Pine to Franklin to Wilson Drive, into Ivy and into the parking lot. Any one of these routes will do. If I'm careful about turns, distances, and so on, each one constitutes a reliable set of directions for getting from H to O. In mathematics, we call a set of directions like this a procedure. What do procedures have to do with computers? Everything. Any job we want to give to a computer must be carried out according to a procedure. Could a computer drive from my home to my office with these directions? In principle, the answer is yes. Of course, we'd have to get a computer with wheels, or at least a new model car with an onboard navigational computer. And we'd have to translate the directions into a language the computer could understand. Right now, it's time for my favorite part of the show, the cooking lesson. Those of you who saw me whip up this glass of apple cranberry juice may remember how profitable an experience that was. Today's topic is the peanut butter procedure. Okay, pretend that you know absolutely nothing about these babies. I mean nothing. You're from Mars maybe, and you don't know what peanut butter is, or what jelly is, or even what a sandwich is. The purpose of the lesson is to enable you to begin enjoying a sandwich like this for lunch. Here's the procedure. Make yourself a peanut butter and jelly sandwich. Not very helpful. If you already knew what a sandwich was and how to make one, you wouldn't need a lesson from me. So let's be more specific. You need a set of directions you can follow. Okay, here's a more explicit recipe. This is peanut butter, this is jelly, and this is bread. Find some of each, put the peanut butter and jelly on the bread, and enjoy. Wait a minute. Some less ambiguous directions might get us closer. Get some bread, peanut butter jelly, and a knife. Open the peanut butter and jelly jars. Spread some peanut butter and jelly on the bread. And enjoy. Well, we're getting there. We really ought to keep modifying the procedure, adding a direction to slice the bread or to buy a different kind of loaf. Okay, let's try again. Get some peanut butter, and we'll get some jelly. And we'll make a sandwich. Well, the procedure still isn't foolproof, but you get the idea. If I'm going to give you a successful set of instructions for doing something that you know nothing about, I have to develop a procedure that's complete and unambiguous. The kind of procedure you'd need has a mathematical name of its own. It's called an algorithm. And since computers don't actually know much about anything, they also rely on totally complete and unambiguous directions, or algorithms, to carry out the tasks we give them. Exactly what is an algorithm? Well, like a recipe, it's a sequence of steps or directions that enables us to accomplish some goal. But that's not a mathematically complete definition. And in fact, the full story turns out to be quite a mouthful. Let's approach it by making a list of the characteristics of an algorithm. First, each step of an algorithm has to be well defined. We don't allow ambiguity at any point. What's ambiguous, of course, depends on what you know. A recipe that calls for clarified butter may be unambiguous for you, but it's not clear to me at all. In the peanut butter example, when we assumed you didn't know anything about sandwiches, bread was ambiguous. Sliced bread would have made things easier. But we're going to see that algorithms are even better than sliced bread. Next, the steps of an algorithm have to be effective. Think about the map again. If my directions say drive across Lake Williams, that step isn't effective. Nobody knows how to do that, at least in an unmodified passenger car. So effective in this context really means feasible. Here's another example. A procedure might call upon you to divide 37 by 59. No problem. Division is well defined and will even allow you to use a calculator. So this step is effective. But suppose the procedure directs you to divide 5 by 0. Division by 0 is a well-known mathematical no-no. So this step is not effective. And in this case, we don't have an algorithm. Third, an algorithm usually has inputs, like peanut butter, but it must always have an output, like a sandwich. Producing an output is essential, but there's more to the story. We want the algorithm to reach the desired output, making the sandwich or arriving at my office, and then stop. That introduces the fourth part of our extended definition. An algorithm must always terminate. Suppose that my driving directions included this step. When I reach the math building, park legally, and come on in. When I arrive, however, there are no legal spaces available. So this new step causes a problem. Now there's a circumstance in which the algorithm won't terminate. What if I modify the procedure this way? Drive up to the math building, find the largest prime number, then come in. Now I'll never get to my office because there are infinitely many prime numbers. Every time I find a prime, there's another step to do, finding the next one. I'm forever stuck inside a procedure that cannot terminate, so it's no longer an algorithm. In practice, we want an algorithm to terminate in a reasonable period of time. If an algorithm doesn't produce an answer in time for us to use it, it's not much help. Take chess, for example. There's a kind of brute force algorithm that will determine whether white can always win. Let's put the pieces back in their original position. Now, there are only 20 opening moves for white. The pawn can move 1 or 2, that's 16, and you've got 2 knight moves on either side. And there are 20 responses for black. An algorithm to analyze chess could examine each of the 20 times 20 or 400 board configurations that are possible after the first pair of moves. The algorithm would figure out all the moves white could make next, then what black could do against all those configurations, and so on. Well, a typical game of chess involves 40 pairs of moves, and that adds up to roughly 10 to the 95th board configurations. Even with a super fast computer, this algorithm would require fantastic amounts of time. Suppose you examine 1 billion configurations per second. It would still take 10 to the 77th centuries to determine all the possible game outcomes. By comparison, the age of the universe is only 10 to the 9th centuries. Even though the algorithm terminates in theory, it takes so long that it's useless in practice. Real computer chess systems have to use a completely different method, modeled more on how human chess masters play the game. Is an algorithm for a problem the same thing as a solution to the problem? No such luck. For example, I have no idea how much tax I owe the government this year, but I do have a reliable algorithm for figuring it out. In fact, here it is. This form leads me through all the steps necessary to calculate the tax I owe. This algorithm tells me the method, but the actual solution only comes by performing the computations according to the algorithm. Can there be more than one algorithm for a single problem? Sure. All these routes meet the specifications for an algorithm, and they all solve the problem of how to get from my home to my office. The obvious question is, which one is best? The mathematician's answer is to ask another question. Best for what? Since I come to work here every day, the best driving algorithm for me is the one that gets me here fastest, in the shortest amount of time. In that sense, we're saying that best means most efficient. But down the hall is a guy in the fine arts department, and he always goes this way because he likes the view. The best algorithm as far as he's concerned is one that produces an aesthetically pleasing solution. Now, when a visitor is in town, I usually give her these directions. It's a longer drive than my route, but easier to follow. The campus entrance is clearly marked, and there's a posted map of the campus roads. In this case, the solution that works best is the simplest one. But if the visitor's Aunt Martha, I send her this way. Since she has to go all the way around Linden Hills, it takes her twice as long as it does me. But not going up the hill saves on gasoline. I'm not saying Aunt Martha's cheap. Let's just leave it that another meaning for a best algorithm might be most economical. You always hear people say that in order to solve a difficult problem, you have to understand it thoroughly. Now we can see that this statement isn't quite true. If you don't know a method for solving the problem, you really have to dig in. Without that 1040, I'd have to learn the entire US tax code to figure out my bill. But if there's a good algorithm handy, you actually don't have to understand the subject itself at all. Just follow the steps of the algorithm in order, and you'll get the answer. That's how algorithms enable computers to solve problems. Computers don't understand the problem, but they are able to follow the algorithm through to a solution. Of course, it's not quite that easy. The algorithm has to be written so the computer can interpret it. That means specifying all the steps in a language the computer can understand. And that's what a computer program actually is. An algorithm translated into a precisely defined language the computer can interpret.
And then the fracture running up into the ilium.
Now, we all know that computers can be programmed to handle an amazing range of tasks, from the lofty, like medical imaging, to the mundane, like printing address lists. But underlying all that variety are a few fundamental procedures that computers do over and over. One of those common tasks is sorting, and computer scientists have given a lot of attention to developing algorithms that tell a computer how to sort things. Without getting too technical, let's say that sorting means putting a list of similar things into a sequence determined by some specified attribute. Numbers might be sorted according to size, for example, from smallest to largest, while names and addresses would probably be sorted alphabetically. In fact, what you sort could be anything. It could be books, telephone directories, or even railroad cars. The computer doesn't care. So we'll use these rods to represent whatever it might be, and we'll sort them according to height, from shortest to tallest. Now, if you were doing this, no problem. Just stand them up, push them together, pick out the tallest one, the next tallest, and so on. But hold on. You want a computer to do this, so you need an unambiguous algorithm that you can program step by step for a computer. Okay, imagine a computer that can do essentially two things. It can compare two rods, and it can move a rod from one position to another. Here's an algorithm for sorting these randomly arranged rods using just comparisons and movements. Let's line these up any way you'll do. And we'll start with the second rod, compare it to the first. It's taller, so it stays there. Take the next rod, compare it to this one. It's shorter. Move it over, compare it to this one. Still shorter. Move these two over, insert this rod here. Go on to the next. Shorter, shorter, still shorter. Move all of these over and insert the rod here, and so on. That's why this technique is called an insertion sort algorithm. You can see that each step is well-defined and effective. The directions tell me to stop when I reach the end of the original row, and the output is this sorted lineup. So insertion sort meets all our criteria for an algorithm. And here's a computer program. The translation of this sorting algorithm into a precisely defined computer language called Pascal. Even though I have to make comparisons and movements over and over when I actually do the sorting, the program only needs to spell out the steps once. And these same few lines work for sorting 10 rods or thousands of rods. Are there other algorithms for sorting a list? You bet. Here's a completely different approach to the problem. Start with the same 10 rods, but this time imagine that each rod is a separate list. Then all 10 initial lists are already sorted. Now we merge each adjacent pair of sorted lists, making 5 new ones containing 2 rods each. The algorithm just tells us to continue this process, merging lists that are already sorted until all 10 rods appear in a single list. That's why this procedure is called a merge sorting algorithm. But when we have 2 items in each list, how do we perform that next merge? Our computer knows how to do comparisons, but each comparison can only look at 2 rods. The trick is to use pointers. Start with a pointer opposite the first rod in each list. Compare them and determine which rod is smaller. Move that rod to the first place in the new list and advance the pointer to the next item in the old list. Then repeat the process, comparing the 2 rods now opposite the pointers. When the number of lists is uneven, like 5, pairing leaves out 1 list. We keep copying that pair intact until the last round, when we merge this list of 2 with the other list of 8. Which algorithm is better, insertion sort or merge sort? Well, remember that we can't answer a question like that without specifying what we mean by better. When we're talking about computers, better usually means faster. After all, time is money, and if you can solve a problem faster each time you encounter it, that may add up to big savings. This is a powerful mini-computer, widely used in universities and in business. I've used it to test the speed of insertion sort versus merge sort. The size of each randomly arranged list is shown along the bottom, and the sorting time along the vertical axis. As you can see, merge sort wins, hands down. To make this race more exciting, I gave the merge sorting algorithm to this small personal computer. Everything about this computer, circuits, memory, and so on, is slower than the mini-computer. By handicapping merge sort this way, we should see more of a contest. Now it's a good race. But for a large enough list, merge sort on a little computer beats insertion sort on the big computer. This leads us to a very important conclusion about algorithms and computers. A good algorithm, even on a slow computer, performs faster than a bad algorithm on a fast computer. In other words, if you want to solve a problem faster, put your money into developing a better algorithm. As we'll see, faster equipment can be important, but mathematical insight is the real key to speeding up problem solving. Do these results mean that you should always use the merge sort algorithm? Not necessarily. There are other factors to consider. For instance, sorting is a data-sensitive task. Which method is most efficient depends to some degree on how the input data are arranged. For example, imagine that your boss gives you a randomly arranged set of 500 index cards containing names and addresses and tells you to sort them alphabetically. You're probably going to start making piles for individual letters or maybe even for groups of letters. Let's see, you've got Hirsch and Banks, Bliss, Price, K. Anyway, when all the cards are sorted into piles, you alphabetize each pile and then stack up the piles in alphabetical order. You may recognize this as a variant of merge sort. Now, let's change the task a bit. Say the telephone company in a small town has hired you to put together next year's directory. Here's the current directory, and your job now is to incorporate 20 new names to proper alphabetical places. Are you going to put the new names all at the end and then merge sort the whole list? Of course not. You're going to find the right place to insert each new name. The point is that for a common task like sorting, there are a lot of algorithms to choose from. Which one you or your computer programmer should use will depend on your particular problem, the nature of the data you're working with, and your goals in terms of time, money, and simplicity. For some really tough problems, the search for better algorithms is bound up with the development of faster computers.
Let's see what's happening right now on the weather map. The weather watchers have phoned in with some good news. They seem to sense that it's going to be nice the next couple of days. They are in the right ballpark. Here's a little cloud mass you see right on the upper Great Lakes moving eastward, and that could just give us a couple of brief showers late tomorrow and on Thursday morning. But basically,
We depend on our local weathermen to look into the future. If these folks came on at 6 to inform us that it started raining an hour ago, weather reports wouldn't last long as part of the news. We want predictions to be accurate, and we want them to keep ahead of nature.
And then tomorrow, I see a beautiful day.
You might think that predicting the weather is a matter of making observations, out the window or otherwise, and then extrapolating from today what will happen tomorrow. That's true. But what may not be so obvious is that mathematics is fundamental to the process. In fact, the foundation of modern forecasting is called numerical weather prediction.
See, they talk about one wave remaining. When you have
The starting point for local forecasters is information transmitted from the National Weather Service in Washington. The NWS collects observations all over the world, from human observers, weather balloons, ships and planes, and from satellites. Twice a day, computers turn all that data into national and regional forecasts. The NWS stays ahead of nature partly by running its numerical weather prediction algorithms on one of the world's fastest supercomputers. Here's a simplified picture of how the algorithm works. The atmosphere is divided into a grid of 256,000 points in three-dimensional space. Observations give 4 basic values for each of these points: temperature, pressure, moisture content, and wind velocity. Now we have a model of what the atmosphere looked like when the observations were taken, referred to as time zero. The next step is to apply a set of equations based on physics to the values at each point. The equations make use of what we know about surrounding points to predict new values for this point 10 minutes from now. Then we do the same calculations for all the other points. This process is repeated for successive 10-minute periods until we can view the model at 24 hours out. Here's a case, then, where the choice of algorithm depends in part on the nature of the computer we're using. The supercomputer used by the NWS is designed for maximum speed on a repeated sequence of calculations, exactly what the weather algorithm calls for. NWS has a research and development team that's always trying to make the forecast more accurate. But accuracy can't be allowed to interfere with deadlines. Changes in the forecasting program aren't adopted until they're proven not to slow things down. Today's numerical weather models are being improved. And thanks to constant vigilance, the calculations do get done in time to get us a prediction. The development of even more reliable forecasts will continue to depend on 2 main factors: designing faster computers and finding algorithms clever enough to take full advantage of them. So is there an algorithm to solve every problem? Unfortunately, the answer is no. Consider equations like these, each of which has 2 unknowns. We're only interested in solutions to these equations that are whole numbers. Using trial and error, we discovered that x = 1 and y = 1 are integer solutions for the first equation. In fact, a graph reveals 4 sets of whole number solutions for this case. But stick with trial and error and tackle the second equation. No matter how long we keep making guesses, all we can say is that we haven't found a solution yet. Although a graph indicates that this case doesn't have any whole number solutions, the proof requires a new idea. You can't get there just by substituting integers into the equation. For centuries, mathematicians looked for a general algorithm that would determine whether any equation like these has whole number solutions. Finally, in 1970, a 22-year-old Russian mathematician proved that such an algorithm does not exist. For other practical problems, we just don't know if an algorithm exists or not. Say I make leather goods, like this wallet and this fancy wineskin. The parts for these products are leather shapes like these. Now, I'd like to cut each of these parts from a large piece of leather without any waste. That means fitting each shape together in a pattern with no gaps or overlaps. Now, it's easy to see how to do that with these squares because they fit comfortably together. Now, imagine a large piece of leather extends in all directions. It's an infinite plane. A pattern that perfectly fills the plane is what mathematicians call a tiling. But it's not clear whether I can arrange these wineskin shapes into a tiling. And I have some new products coming out that also have irregular shapes. I'd like to have an algorithm that will tell me whether any particular shape can form a tiling. Well, so far at least, I'm out of luck. We don't know if such an algorithm exists. It hasn't been discovered yet. But mathematicians have also been unable to prove that it doesn't exist. At this moment, the existence of a tiling algorithm is an open question. Now, algorithms, complete and unambiguous procedures, are essential for solving problems on computers. And with respect to algorithms, we've encountered 4 different kinds of problems. Problems for which many good algorithms are known. Problems for which better algorithms and better computer techniques are leading to better solutions. Problems for which we can prove there are no algorithms. And problems for which we don't know if an algorithm exists or not. And here's the kicker, something I respect because it keeps us mathematicians properly humble. There is no algorithm that can determine which category a given unsolved problem belongs to. In other words, there is not and cannot be a granddaddy algorithm which proves or disproves the existence of an algorithmic solution for a particular problem. For this reason, the applications of mathematics to computers will continue to be an experimental science.